of the name of the section is convex-affine and linear combinations of vectors, but really, because we speak of linear algebra, so then it is really limited to linear combinations, and the rest are just there to why particular kinds of linear combinations are convex and affine combinations. So in linear algebra, we stick primarily with linear combinations, even though sometimes they just don't make sense, because if they are weights, the whatever is being weighted together should have positive weights. Okay, so you cannot combine, and that's what I mean. You can combine two things on a scale, and then hypothetically, the weight could be negative if you're actually pulling in the opposite direction. So you can hypothetically combine things in that matter. With anything more practical, such as mixtures. It is not, you cannot have a negative amount of something, typically, say coffee. Okay, even with the example of so mixture of mixtures is what we're really talking about now. So you cannot have a negative amount of, or in this particular case, of a particular stock, for example. Okay, so maybe you can make a sense of it with some kind of debt versus credit, but really maybe not. So, but in the abstract theoretical mathematical sense, we can combine any vector with any coefficients, and that's what a linear combination is. So any number of vectors can be taken together, and we can produce a linear combination of them. And then what we're really after here is we've seen examples why it is why we try to solve the problem in that manner is literally linear combinations of some basis vectors produce all vectors. Okay, but if we take other vector, maybe that's not going to work out. So because it's a mixture, each vector is a mixture in the first place. Okay, a mixture, a linear combination of the basis vectors. So each of these linear combination of E1, En. Okay, so then we are speaking of linear combinations, or mixtures of mixtures, and then we ask ourselves, if we take all the linear combinations, what do we get? What do we get in that sense? And what we saw examples that we have saw in lower dimensions. The question is quite revealing, and that in lower dimensions, if you take a linear combination of vector with itself, all you have is the multiples. If you have two vectors and you start doing linear combination, it depends. If they are parallel to each other, you're in the same place again. If they're not parallel to each other, then what you're going to end up with is a plane. So that's the example. So where A not parallel to B. Okay, so then linear combinations produce plane. So that's a way to produce. What is that we have produced? We produce vector spaces. So multiples of a vector give you a vector space, one-dimensional. Two vectors that are not parallel to each other produce a vector space. And then they go on. It would have three vectors. Three vectors also, if they're not in the plane, that together they will produce a three-dimensional space. So it is called span, linear hull, and also known as span. Okay, and then once again, it is a way to produce vector spaces out of in a bigger space. Doesn't matter how many, depending on how many vectors you start with. No matter what the dimensionality is, it will produce a bunch of vectors. So vectors as linear combinations, and together, taken together, it is a whole subspace. So once again, the picture may be not giving you giving credit, but if I take those two blue vectors, naturally I get this as the average, right? Say average. But then I could add them, get this. I could take the average. I could take multiples of each of these. Okay, and then I take a negative of each of these, right? And then I start adding these together, all together. So that's in that manner. That's how I'm going to end up with not everything. It seems like we are in a three-dimensional space here, but if I stick to those two blue vectors, I will not gonna produce any vectors outside of that plane. So if the two vectors are contained by the plane, then all the linear combination will also be contained within the plane. And together, it is the plane. Okay, so that's later to be discussed. Multidimensional spaces gives you extra challenges. As you can see here, it's a whole table of it's still only two vectors, but the space is 40 dimensional. Okay, so once again, it is like a plane a table of vectors. Okay, so all right, so linear combination. So once again, the going back to the basic where we came from, and that is every vector is a linear combination of basis vectors. And so the question becomes, what can serve as a substitute for basis vectors? Okay, and so like I said, you can take basis vectors, so any three vectors like this will serve as a substitute. Okay, substitute meaning that can be other choice for E1, En. Okay, and once again, you could that's example from calculus that I brought up at the end, that every polynomial is a linear combination of the power functions. Okay, so if we stick to dimension n, if I take all the polynomials, unfortunately that will be an infinite dimensional space. So let's just stick to a dimension that's not infinite dimensional, so that every polynomial has n plus 1 numbers that determines it. And conversely, any n plus 1 numbers from a naught to n will give you a polynomial. Okay, so that creates a space. It turns out that it's like such a thing as polynomials actually is Rn plus 1. Okay, so you can do differentiation integration within that space entirely. So it's a kind of elementary calculus. And but also it's interesting that you could do something else. So this is a linear combination of the power function what if, and that you see in the in elementary calculus is the center. The center might be different. What if I take 1 x minus 1 first power, x minus 1 second power, x minus 1 third power, and n of them. Okay, so in other words, the center has been shifted to 1. Okay, so and then once again, it still works out. So works too. So you could think of this as a basis, as a standard basis, but this is also a basis. A basis. So in other words, in the sense of what this is, every vector is a linear combination of basis vectors, and I guess a second half of the punchline is that that's the only way. The only way to represent it. Okay, so not only every vector can be expressed as a linear combination of the basis vectors, but also there's only one way to do it. Naturally, if you already that's the y coordinates work. So any combination of numbers gives you a location, and the location will give you a combination of numbers. So the same with vectors. But as we know from geometry, you can choose different Cartesian system for your plane or space. And same story works in vector algebra, except we do not speak of axes. We speak of basis vectors, bases. So one basis is standard basis, then there are alternative bases, and they have to satisfy this condition. So that's what makes a basis. That's what make a base. So the basis, the standard basis, the standard basis, the standard basic vectors. But these are another combination, yes. And once again, you can see how we can do it even in calculus. Okay. Okay, so some examples. Okay. All right. So let's take a look at certain things in n-dimensional space and how we can start getting things such as let's face it, calculus if we want to. We still stick to straight. Everything is straight, but nonetheless, that's a way to start doing calculus in n dimensions. So let's just quickly point out what a straight line is in n-dimensional space. We already know what the answer is. Generally, it is how do you create a straight line? You take a vector and then just go multiples of that vector. So that's the basic idea. But a parametric curve is something more specific. You have to have a function. Okay, so it just happens to be a function that model 99% of the time models motion. Okay, so then the input is time, and output either location or in the case of vector algebra could be say velocity, could be acceleration. Okay, so location usually thought of as a point, and the velocity acceleration usually thought of as vector. So that's why we are we are looking at it. Okay, so that's the function as a black box. Remember that we when we did pre-calculus here early on, that's we're still using that idea. So we have to present the function and in that manner. And as you can see, once again, I'm trying to use the that convention that uppercase letters stand for vectors or points, multidimensional stuff, and lowercase for numbers. Okay, so in that specifically, then generally speaking, the function goes from Rn to Rm, and so later, right now, the simplest case is in fact the input one-dimensional. So once again, motion. Time comes in, and for every moment of time, you are somewhere, and that somewhere might be multidimensional space depending on the situation. We are moving through physical space. We're moving through kind of a space that is more um, synthetic. So we may make it up. So we saw this picture already before, but this one is specifically limited to linear algebra. So once again, there is we have a function from Rn to Rm. This one, okay, and so so the dimension of the inputs of the domain and the dimension of the codomain is m. And then once again, what you get familiar with in calculus 3 primarily are these functions. They are all there surely are curves or surfaces in those spaces. So we're looking at everything straight. And so then calculus 1 is this. This is calculus 1. Okay. And then you can progress to the right if you want to deal with the function of multiple variables. So we are instead going into this red one. So we're moving in higher dimensions. So the domain remains one-dimensional, as you can see, is moving upwards in that table. And so then the parametric curve in the one-dimensional, in the context of linear algebra, is a straight line, which you can see right there. So it will be a multiple of vectors, and so we just want to write it out. So the variable is real, and the values lie in the dimensional space. And so this is the only problem is with this idea that I already suggested is this works out if through the line through the origin. This is the origin. If we are looking at the straight line through the origin, that's exactly what we do, just multiple of the same vector. If not, it's slightly more complicated. So the origin is at the bottom there, bottom left. So how do we plot this line? The answer is affine combinations. So we already had that idea before. So affine combinations of two vectors will produce produce the blue vectors. All right. So remember, affine combinations add up to 1, but do not adapt to 1, but they don't have to be necessarily positive, lie between -1 and 1. Okay, so if they are between -1 and 1, those are convex combinations, and they stay within U and V. Because we allow them to be negative, we go to the left and to the right, and so we end up with a bunch of vectors going into all directions, into both of the directions. And if we trace the ends of those vectors, they actually form a straight line. Okay, so that's what we're looking at here. A vector of the form alpha u plus beta v with alpha plus beta equal to 1. And once again, each corresponds to a single weight. When alpha is equal to 1, means beta is equal to 0, and we are here. When beta is equal to 1, alpha is equal to 0, then we are here. And then negative alphas are here, right? And negative betas are here. Okay, and both alpha and beta between 1 and 1, 0 and 1 are in the middle. Okay, so that's how it goes. Alpha negative, beta positive, then both of them are positive, but between beta becomes negative. Okay. And as you can see, the purple line is indeed a line, and so that's we just need to take that algebra and translate it into the language of a function. So alpha is the parameter. Remember, parametric curve means that there's an input, and then what we are tracing here is not the vectors. You know, as I said, you imagine this is a process already. if you imagine that so how do we turn it into a process, a motion, if you like, a motion, and the answer is we have to identify one single parameter. We have two. It seems like we have two parameters, but in reality, because they are connected, beta is equal to 1 minus alpha. So this is better. Okay, this is better for our purposes when we speak only of two vectors. So it's a linear combination, but only with two vectors. So we can just let's just get rid of one of the parameters, and we have alpha u plus 1 minus alpha v. Okay, and then it is a process. So it is a process, and that is in the abstract. It depends on alpha. So each alpha will produce a different x. And then what is it? It's a function. So alpha gives you every real number gives you x of alpha, a vector. So real number, and this is vector in whatever dimension. Okay, so that's that. What is it? Is this? So this is what we're seeing here. What is its parameter curve? Yes. Okay. So and so well, that's pretty much it. Yeah. Yeah, so then particularly if you're interested in actually finding the vector that goes along the line, the simplest one is to pick the vector, subtract. So you might not be visible, not exactly visible here. So let me try to plot it here. So this is the vector. Okay, so there, and remember, for the to set up a line, you need a point and you need a vector. So the direction of vector is once again u minus v, or v minus u, doesn't matter in this case. And then take one of the ends of these vectors as the starting point. And so altogether, that's you have your equation. This is in 4 dimensions. 40 dimensions. That, as you saw, remember, once again, this is a line. Okay, so let's be clear. What we're looking at is a line in the 40-dimensional space. Okay, so it's a graph. So 40-dimensional space, it's 40 numbers. It's a sequence of 40 numbers. If they're in any way related to each other, it translates into a curve. And then what happens is you are transforming as this curve is gradually being transformed. It produces this kind of effect. Okay, so that's a 40-dimensional space. So and the point. So the picture is probably worth comparing. So what we're looking here at is vector v and vector u, green and red, and the line passing through them, and it is in purple. So similarly, you can see the green and the red are the two vectors. They're vectors, single vectors, and then the line is made of a bunch of vectors, and these other vectors are now in purple. Okay, so except having an arrow, when it's on the plane, it's very clear how to visualize it. And this is in 40-dimensional space. It's a sequence of numbers. Okay, so but the gradual transition of one into the other is an interesting part about it. And so I guess it is kind of a visual. And you can imagine that what's going to happen if you continue on. This is only like a 10 or so points or vectors on the line. If you keep going with that, what you're going to get, you get more and more of the extreme like this, and then more and more, and there is no stop, and over here like this, there will be more and more. But if wherever the 2 points are equal to each other, then these combinations will produce the same value. Okay, so they will still pass it through that point. So we're not going to get every single curve that's imaginable. So they will kind of resemble the two original ones, but in a more extreme way. Okay, so any questions about this? Okay, so once again, the variable is time, the value is location. It could be a point, could be a vector. But ideally it is a point plus a vector, as we have the way we have done it. So this is your original pre-calculus way of a straight line in one-dimensional space. It is x depends on y, so it is one-dimensional, even though it's usually drawn on the plane. It's one-dimensional because the space where things are happening, which is the codomain, is one-dimensional. So that's the dimension of y, and the parameter is x. Okay, so then what is happening here is you are at B. So when x is your parameter, x equal to 0, y is equal to B. So that's the starting point. And where is the direction vector? Okay, so once again, if we try to apply the logic what we have here, so point in on the plane, this is what it looks like. Point P naught is the initial location, and then there's a vector, say V, in which you go, and then from these two things you build your line. Okay, so if we were to go backwards, rather than going to high dimensions and complicate things, we go back to lower dimensions, and then what does it look like? And it doesn't look like that at all, because this we are moving along the y-axis. So the starting point is here on B, and then the direction vector is in fact the slope. So direction vector is M. Okay, so that's what it looks like in one-dimensional case, because everything is nothing but a number, not a point really, not a vector. So a vector is a number. So you are at B, and then you're moving in the direction of M. Okay, so that's what the slope, so the meaning of the slope is. So then this parameter curve, once again, let's get back to that two-dimensional case. This is the vector 2, 3, and you just start multiplying by a vector one at a time, adding them together, but then you also take proportions, smaller proportions, so you can add half of that vector and so on. So the red dot is where we are, and then we can proceed 2, 3 at a time, or we take half of them. Okay, so in the effect is the same, and this is the formula that we already saw. So once again, naturally it is multiplication. Okay, and so the initial the way we understand multiplication initially is that it's a repeated addition. But when t is equal to 1 to 3, then this is repeated addition. But also in the case with vectors, there is might be slightly different, especially when t is equal to say 1/2, or it is pi or whatever. Then it is a stretch. So one vector being added to itself, and you have one b to the and so on. With fractions, you have to think it slightly differently. I think in terms of the stretching, including the flipping, because negative values will point it in the opposite direction. So then naturally you can split it into horizontal and vertical. So if you here you can speak of motion, with no regard for a particular representation of a particular Cartesian system at a particular basis. Because vector v could be expressed at point P and point V. These are the two V naught rather. So they are here expressed in terms of in this particular basis, right? So it's 1, 0, 0, 1. But what if I could also choose a different basis and go with the 2, 0, and say 1, 1? Okay, so that also just as good. The representations will be different, but the algebra is the same. So that's the good thing about the algebra of vectors is the same no matter what the Cartesian system is chosen, because the way we have decided. Okay, so but nonetheless, if the system is supplied, then we go back and we split the motion into two components, and that is so typical in say physics when it turns out that the motion with respect to x, motion with respect to y can be treated entirely separately, like an object thrown forward. Then indeed there's a gravity in the vertical direction, and there is no gravity in the horizontal direction. So you just look at them in entirely separate fashion. In this case, it's not even that, because the motion is straight. There is no force. Okay, so you can think of it as the first, rather than thinking about this. Which one is the third Newton's law, which involves forces. This is like the first Newton law where there are no forces. Okay, so and then once in motion, it tends to stay in motion. Okay, so that's what it is. So the motion is the vector 3, 2, and then that specifically stays not just stays in motion, it tends to stay in exactly the same, if it makes sense. So not just to say that an object in motion it tends to stay in motion, it surely makes sense. But if you want to be specific, you have to also say that the motion it tends not to change. So if you were moving it to 3 at a time, to vector to 3 at a time, initially, so you tend to continue on with that 3 at a time, exactly same direction, exactly same speed. Okay, so that vector of your velocity, which is what this is, will remain the same. Okay, so that's the good news. And then what changes your direction? That's the force. You need a force to change your direction. You need a force to accelerate or decelerate your motion. Otherwise, that's what it's gonna be. So you can imagine, the universe that made up with no forces and just objects moving in all in straight lines, and nothing is happening. So that's if you can imagine that. Okay, so once again, these my formulas. So just the algebra that needs to be carried out in order to recompose our vector notation from the one-dimensional notation is once again. So x's and y's are initially treated as if they're separated by a wall. Okay, and then so linear behavior with respect to x, linear behavior with respect to y. The formulas are written. Then they combine together. That's not too complicated because you just combine them into a single vector like this, right? Combine them together, and then it's a single vector, and which is fine, right? So we can write that answer right away. I do right here. Okay, so that would be, this is a parametric representation of my curve. Okay, there's nothing wrong with it. The problem is of course we are not utilizing what we have learned, and what we've learned is the algebra of vectors. Okay, so then what we do here instead, we are decomposing it. We are finding the algebra. So what algebra are we supposed to find here in this formula? Vector algebra. So let's say this is a vector. What is the algebra that we're supposed to see here? Well, just to refresh your memory, 1, 2 plus 3, 5 is equal to 1 plus 3, 2 plus 1. That's, so it looks familiar. This addition of vectors, component wise, reading from left to right naturally. Now pause for a moment and read it from right to left. This equation reading from right to left, from the summation to backwards. So this is the summation, algebra executed, or backwards is the decomposition, right? So for whatever reason, you may want to break your single vector. The vector is right there. It is 4, 8, right? This vector is 4, 8. For whatever reason, you may want to break it apart, right? Represent the vector as the sum of other vectors. Okay, so naturally, this one is arbitrary here. The point of the example is just to remind you that every equation can be read from left to right and from right to left. So if you have executed addition of vectors many times, then at some point you might have to go backwards and reassemble, disassemble the vector. So I want to disassemble this. So what do I do with this? Okay, so you can see if we read from right to left once again, then what is it we're seeing? We're seeing two additions that turn into one. So two additions within each of the components of the vector become one single addition of vectors, right? That's what you see on the right. So I'm in the same place here. I have two additions. So can I disassemble it? Or maybe if I write it in the columns notation, it's better. 1 plus 2t, 3 plus 3t. I want to disassemble it. Replace 2 plus signs with 1. Can we do? That's right. 1, 3 plus 2t, 3t. Okay, right? So we're utilizing vector algebra to we are discovering vector algebra in this. The algebra is plain, the numerical algebra, right? Because every component is nothing but a number, so we can do any algebra within it. But as a summary, if you prefer, that's one way to understand what has happened here. This is a summary. And if you have addition in the first row, in the first entry, in the first term, the first component of the vector, then and in the second, then it means that the addition can be actually executed only once in terms of the vectors. Okay, is it clear what has happened here? And then what can you see the point? Can you see the point? Why we did it? Look at that 1, 3. What's the meaning of 1, 3? It's a vector that the initial starting point of my line. Okay, so which may or may not be exactly visible, but it surely is now. 1, 3 is where we start. It maybe it will become clear if we take one more step of this assembly. If we look at the second vector over there, 2t, 3t, can we simplify it? So I have 1, 3. I'm sorry, 1, 3 plus what? No, not cancel, but what can we do with t? Factor it out. So what do I get? Right. Okay. So literally, so we just did it with summation, right? So we did it with summation, right? 2 additions right here turned into 1. Now we had 2 multiplication by the same number right here. 2 multiplied by t, multiplied by t. So let's just multiply by t once. T is a number, so if each of the 2 components of the vector is multiplied by t, it's the same as if the vector itself is multiplied by t. That's the meaning of scale multiplication. We surely made that operation many times, except we always were the other way from vector multiplied by number. What is it equal to? That's what it's equal to. But we also frequently go in the backward direction to discover things, and this is the representation of my line. Very effective. It gives you number 1, 1, 3, the initial location. I also have getting my 2, 3. Right, that vector 2, 3, the direction vector has also been discovered in the representation. So this is the starting point really. Okay, and then we made this discoveries that if we combine these 2 into vectors, then the structure of the line emerges, which is not to say that it is new. So compare the compare once again say, yeah, the structure of 1-dimensional, 2-dimensional cases are the same now. So once again, if I look just at the left hand side, left, the first one, x of t is equal to 1 plus 2t. What does it mean? It means that once again 1 is the initial place, and 2 is the direction vector. Okay, so if I were to match things, no matter what the dimension is, including the dimension 1, it's always the same. Point plus a multiple of your direction vector. So here, point 2, 3 plus the multiple of the direction vector. The point is 1, 3. The direction vector is 2, 3. But in the 1-dimensional case, it's the same story. You really look at it, this equation, right? If we look at this one, it's the same thing. 1 is your initial point, and 2 into t, what is it? It's 2, your direction vector multiplied by t, the multiple. And so here you're moving 2 at a time, okay? And here, because it's 1-dimensional, so you would just keep adding the same number. Or now we are the structure is the same. Well, the algebra looks very much the same, but now we're dealing with vectors. Okay, so then the idea then is that indeed it will once we get rid of the specificity of dimensions or specific numbers, the vector equation will be applicable to any dimension. And so this is the computation we just carried out, but the punchline is here. Okay, so it is once again the dimensionality has disappeared, and we have P of t. Our parameter curve is equal to P naught plus TV. So P naught initial point plus the multiple are multiples, whatever multiple is, of the direction vector. Okay, so then that is applies to every single vector. So like I said, sometimes this is it done that computation is done in the string notation with brackets, but I do think that it seems to be much easier to discover what we're looking for when we write them in the column notation. The vectors in the column notation, like I have here, it is predictable that how you split it, right? So you're looking at this and you realize that the pluses appear twice, and then you might cut the whole vector into two along the plus sign. Okay, that's what the first stage happens, literally kind of split the vector into two along the plus sign, and then once again you can see t is repeated. It's not going to cancel, but it will get factored out. Okay, so that's the second step, and t gets out. And then we end up with this formula, and once you do it a few times, you use it as a formula, represent every single line in every single dimension. Doesn't matter. The interpretation, once again, is fairly, if you want to speak of motion, which is, let's face it, 99% of the time, this is about motion. Parametric curve is about motion. So V then stands for the velocity. Okay, so P naught is your initial location, because when you plug in t equal to 0, you get P naught. And then it just t is time, and you multiply velocity by time. What do you get? You get displacement. Okay, so yeah, so this is the displacement. Okay, so your current location is your initial location, what this formula might be. Current location is equal to initial. I think that may be written here. So yeah, here it is. Okay. Initial position at time t, initial position plus time t times velocity, which is also known as the displacement. Okay, so that's the way it works out. So once again, positions could be probably better thought of as points, and then velocity definitely as a vector. So once again, if you write these out in dimension 1, 2, and 3, I didn't actually write, so let me write in dimension 1 here. Pi, I'm using lowercase. P of t is equal to a plus t u. Okay. Okay, so that's what the parametric curve in dimension 1 looks like. And then dimension 2, 3, you just every vector becomes longer and longer. And then why bother and write them in that notation when the vector notation provides us with a way more compact representation. So that's how we write a straight line parametrically based on the idea of motion along the straight line. So the line itself is the road. Let's be clear. This is the road. And this is not the road, this is the track. Okay, so because it involves time, right? So you can have the same road driven by differently. Okay, so hypothetically, so that's one trip, our trip. Well, okay, so as an exercise, opposite direction. Same road. What's the formula? Where? Oh, yeah, negative. Instead of plus, we have minus. That's right. So because so P of t is equal to P naught minus TV, meaning that's if you want to elaborate why it's the case, P naught plus T times negative V. So your velocity is the opposite. So what V, negative V, what do they have to do with each other? It's same vector pointing in the opposite direction. So you're driving along the same road, but with the same speed, but in the opposite direction. You can replace also. So if you that's one answer in the opposite direction. Another one, twice the speed, you replace v with 2v, so p naught plus 2gv. So you are moving twice along the same road. The trip is very similar. You're just driving twice as fast. Okay. So once again, keep that in mind that the curve itself, well, it's not a curve, it's a straight line, but nonetheless, is what you actually see. And then you can move along of it. So there is no t. So this one is say maybe in R2, it is a plane, and on it there is a straight line, and then we can move along that straight line in infinitely many ways. We're not trying to do any acceleration. So, but even if you do not allow for any acceleration, nonetheless, you can move it very differently depending on your velocity. And so velocity, as long as velocity is aligned with the direction of the road, you can drive anywhere you want. You can drive in both directions as well as you can drive fast or slow. So if you like, that formula is, you can call it the point slope formula. So if you remember point slope form in one-dimensional case, that's a similar thing. And we do not use slope y-intercept form because there is no y, there's no y-intercept, so that's why point slope is more appropriate. And then the slope is, that to be clear, that the slope is in high dimensions replaced with the direction vector. Okay, so the slope, which is a single number, is sufficient to describe the direction of the motion of the line. But in high dimension, you need a whole vector. Okay. So just to remind you, that's how calculus operates. In case you are, well, you have taken calculus 1, everybody here. So that's what happens. You zoom in on the curve, so much so that until it becomes straight line, in which case the linear algebra applies, and you find the tangent line through differentiation, and then everything is linear from that point on. Unfortunately, that formula that you find for the line, the formula for the line that I spoke of, is in fact what we just found. Okay, so except in dimension, might be more dimensions than this, which is 2. The problem, of course, with calculus is that there will be different lines for each point. You move to the different point, and your line is different. Your tangent line is. Okay, so recursive formulas, we talked about that already. So you can represent it. You can actually plot it. So similarly, let's take a look at the multidimensional space and what this motion would look like. So this is what the motion would look like on the plane. All right, so literally, if you are given a point, you're given a vector, and you don't want to do algebra by hand, you bring a computer and you do this, right? So if you look carefully at here, so you have 2 values to worry about, and then you choose your unit of time that you consider small enough. So here we have chosen to be 0.5. And so 0.5 at a time, we use 2 formulas, x and y are progressing independently. And then these are the iteration, this is the time, and then these 2 numbers these taken together, they're being plotted. So literally, if it is an Excel, highlight the 2 columns in your spreadsheet, plot them, and then you end up with a bunch of points like this. Okay, so that's very predictable, and but well, hypothetically, if you were not doing actual motion, but rather doing on motion in physical space, you're doing motion in some kind of a made up space of data. Okay, so such as in this case, maybe prices of stocks and bonds, commodities. So it is a 10,000 dimensional space, let's say, and then but nonetheless, the rest is exactly the same. So except having 2 formulas, you'll have 10,000 formulas to keep track of each of those 10,000 prices. And so if you're lucky, the development in all directions is actually linear. So that's the simplest dynamics that you can imagine, is a linear dynamics. And so hypothetically, that's exactly what you see, even though they surely might be moving at different rates. So each of those quantities, 10,000 quantities, changes linearly, but a different rate. Okay, so how do you even do it? It's, as you can see, it's a large spreadsheet. Okay, so really large if you think about it. So each column represents that particular commodity or stock, and then it is developing in the with time going down in the so time is vertical and the stocks are prices rather are horizontal. Okay, so each column depends presumably in independent fashion. Now, how do you visualize it really? So the computation presents no trouble whatsoever if your computer can handle it. So just add the number, look at it. This is the formula, you just execute this for each column of your spreadsheet, you execute that, and that's what it does, and it goes one at a time in the vertical direction. So visualization becomes a problem because at best you can visualize only even if you have three-dimensional capabilities, which Excel does not. Then you still can only do three at a time. So you can do two at a time. So that's the limitation of the whole thing, and that's why algebra is indispensable. Is that all the data is here, right in front of you, so it's a table of numbers. Let's say that this indicates seems to be have only 9 stocks here, okay? But even then, not only 9 stocks that you want to follow with the follow the dynamics. How do you visualize? And the answer is that's how you can only do 2 at a time. So if you have 2 at a time, highlight 2 columns, the first and second, and then you have how the 2 of them depend on each other. You can do 3 and 4. Once again, how they depend on each other, but nothing beyond that. So that's the unfortunate reality. So these are, the motion is in the 10,000 dimensional space, and these are like the shadows or projections of that straight line on the coordinate planes of my multidimensional space. Okay, so and that's the only thing that we can see. Okay, so once again, stars, bonds, body temperature, blood pressure, pulse, and breathing rate combined together, for the vital of a patient possibly, and so the story would be exactly the same. If you naturally the way they visualize it, you know how they have a bunch of graphs. Okay, so that's how it is normally visualized, whether it is stocks, bonds, or it is a medical profession. A bunch of graphs going together, and then you're supposed to, in your mind, combine them into one big picture and one dynamics. So, well, it's not surely not easier than just but it is inevitable. It's those functions that we saw that they are each of which is one single number, but it's changing with time, and so this is a harmonic curve nonetheless. And so just you don't expect to be linear, so we're not going to be concerned with that. Okay. Okay, so that's the okay, so I'll skip that. Runs over the run. So remember, once again, if we want to connect our two-dimensional case to a one-dimensional case, and the slope is rise over the run. Okay, but on the other hand, so if you take a careful look at this little computation, so this is surely familiar, and if you're still hazy about the meaning of the direction vector, that's what it is. Okay, so it is instead of dividing rise over the run when y depends on x, that makes sense when y depends on x, but when they do not, so here x, y depend on t, then you don't want to combine them necessarily together, and you're not concerned. There's no x that comes before y, but rather you are moving along that road. Then you literally take run and rise and then form a vector. That's what you see in the middle here. It is a vector, and that vector is the direction vector of your line. Okay, so once again, calculus 1 and everything related to it. That's how you do the geometry of lines. Straight line, rise over run. That's all there is to know. Once again, rise is on the y-axis, run on the x-axis. And that's it. But if you were to think about high dimensions, that's not going to work anymore because they're just 2 numbers. So what do? You form vector. So you start thinking ahead, and you form a vector, and in this case just 2-dimensional, but nonetheless the 2 numbers, the increments of x and y, run and rise, form together a vector, and then that vector points along that line. And then now once you take the right route, okay, so once you understand that this is what we do, we pretty much abandon that and go this way. Then from here we go to dimension 3 and on in high dimensions as well. So once we understand vectors, then we understand straight lines as well. Okay. All right. Okay, so from algebra to geometry. Okay, um, we're trying to keep them separate, as a matter of fact. So it's not as much as possible, because they're complicated. So if you can do algebra without geometry, well, do it. If you can do geometry without algebra, do it. And so, especially when you progress to high dimensions, and they are not exactly go along with each other as well as in dimension one. So algebra and geometry of numbers, you might have trouble actually distinguishing them from each other. So why do we care about geometry so much? So algebra, remember, it is primarily addition, subtraction, and scalar multiplication. Okay, times k, for example. Okay, so all we have done up until now in this multidimensional space was algebra. So geometry is about measuring. Remember, so geometry and algebra. So any real numbers have both of them, and vectors have both of them, right? So vectors, and we did that geometry we already done with points. With points, it's done. Now we're doing them with vectors. Okay, so why do we care? Well, obviously we want to understand these multidimensional spaces, and in addition to understanding the algebra, we want to understand the geometry. But the one thing that we cannot do without geometry is calculus. The algebra will not do. Limits. Remember limits. To understand derivatives and integrals, we need limits. To have limits, we have to be able to speak of convergence. What does that mean? It means that points are getting closer and closer to a particular value. Numbers converging to a particular value. You have to be able to speak of how close we are to that value. The algebra does not answer that question. Okay, so so convergence is what required to in order to do any kind of calculus. Okay, so that's in linear algebra responsible for both this and that too. Okay, so magnitude of a vector is not a complicated idea. It is very similar to the distance between points. After all, a vector is a directed segment, so it has a beginning and the end, and therefore we can simply measure the distance. But to keep in mind that that number will not be describing the whole thing. It will be describing whatever is the magnitude and the direction is the two attribute of direction. Is the two attributes of a vector. So it's very easy to understand what magnitude is, and then we ask ourselves what the direction is, and the answer will be whatever is left. Okay, so if you take the magnitude out of consideration, then what you left is the direction. So let's do the magnitude. Okay, so the magnitude of a vector is what's left of it when it's stripped of its direction. Okay, so as if you want to think about it in terms of motion, probably makes sense. It is velocity without direction. There's a word for it. Speed. The speed. So what your speedometer, not velocitometer, but the speedometer, it doesn't matter which way you go, it's the same speed. Okay, so you can do it in dimension, then naturally it is, at least the car doesn't even know about direction. So car thinks you are one-dimensional because you're drawing on the road. You might be driving in roads, you might be driving up a ramp, but the car does not know, the speedometer does not know, and so because it measures only how fast those wheels are turning, and so indeed the direction is stripped off. So once again, speedometer. No direction, no dimensionality, all of that is lost. The idea then how to get to it is very simple, because if we understand the points and distances, and so then remember with the metrics that we talked about, how in multidimensional spaces there are several ways to compute the distances, and then whichever it is, it doesn't matter. That's what this is the step is right here. So we just, if there is a vector, we look at this its initial point and the final point, and assuming that our n-dimensional already equipped with the distance, the meaning of the magnitude is quite clear. Just the distance between the two endpoints. The notation is those two vertical bars, which you can guess why. Why two vertical bars? Because of the absolute value, right? So the absolute value, the analogy is total, the total analogy. So, so in one-dimensional case, the magnitude is the in one-dimensional case, the magnitude is the absolute value. So the magnitude of A is equal to A. Okay, so we're just going to try to, so once again, that's the meaning of the absolute value, how to get rid of positive and negative, which means stripping off. There, in dimension one, there are only two directions, positive and negative. How do I get rid of it, of the direction? And the answer is just use the absolute value. So lose the plus minus. Okay, so which is the direction. So that idea is totally now applies to infinite dimension as long as we know how to measure distances. And yeah, so the same distance. So every other point on the circle or in sphere in high dimensions will have the same distance. So that is clearly, yeah, direction is lost. Okay, so at every point, the same distance from the origin will have the same magnitude. So yeah, we don't care about the direction at all. So any metric is applicable. So once again, remember we have three main ones, and so but primarily, or surely, as we see later, the Euclidean metric remains still the vector for our purposes. Okay, so the magnitude or the length of a vector in Rn with metric d is defined to be the distance between its initial and terminal points. That's it. So once again, that's the convenience is we don't have to specify what the distance is. We don't have to think about is there a square root. If I don't remember the formula, I still know how to deal with the magnitude. The norm is another word that we use for it. So absolute value, I talked about that. Once again, there are three distances: Euclidean metric or norm. Then we have now Euclidean norm. We have taxicab metric. We have taxicab norm, and we have sup metric. We have sup norm. Okay. So once again, we try not to be specific about which of these curves we use, and which let's try to just say without using those subscripts 1 to infinity, and just deal with whatever it is. Remember, we have properties. We have properties of the distances. Okay, remember the three properties of the distances, and then to begin with, let's see. So distance is any distance, any metric. Will have these three properties. Okay, and those three properties, they are the ones that we're going to be using in order to understand the magnitudes, the norms. Okay, so then it would matter then which of the distances we pick. So ideally, that's the ideal situation. So for a while, it will work just fine. So number one property is the positivity. Okay. So the distance between 2 points cannot be negative, and it is equal to 0 if and only if that these points at the same point. Okay, let's translate into vectors. Once again, based on this formula. So that's the definition of the magnitude of vector, and this is the and so this is the property. So the if we were to translate this into vectors, then we speak of the vector PQ, right? So what is that? What can we say about the vector PQ? And the answer is just rewriting it, it's exactly what this is exactly it, and this is exactly it. So in reading it, we're saying that the magnitude of a vector cannot be negative. Okay, that's fine. And it is equal to 0 if and only if it is the initial and terminal points are the same. Okay, so that's a fine way to rewrite it because that's exactly what we did. But there's a way to simplify it because when P and Q are equal to each other, then the vector is nothing but 0. Okay, so there is a more effective way to rewrite it. This is This is what I don't want to think in terms of endpoints anymore. P and Q, let's just say we have a vector A, and then number one property, once again, the positivity property is that the vector, the magnitude of the vector will be negative, and it is equal to zero if and only if that vector is zero. So the only vector with zero magnitude is zero, the zero vector. Okay. So once again, we took the first property of metric of a metric space, and then translated it in the language of norms and magnitudes. The second property is symmetry. The symmetry, so the distance from P to Q is equal to the distance from Q to P. Okay. Once again, I can rewrite it in terms of vectors and magnitudes. It's exactly what it is. This is equal, and this is equal. So the magnitude of vector PQ is equal to the magnitude of vector QP, but we could be more specific if we were to draw by once again using this as an idea. So we don't want to use in terms of speak in terms of endpoints. It is actually the PQ and QP are in the opposite direction. So in fact, it's a negative one. It's not they are not equal. They are pointing in the opposite direction. So like this. So P and Q, from P to Q to segments. Then we have a vector QP and PQ. They're pointing in the opposite direction. So if once again, if we forget about the endpoints, we speak of A and negative A, and they have the same magnitude. Okay, so once again, very predictable conclusion, but nonetheless, for the record, has to be stated. So later on, we can use these as tools. So once again, the magnitude of the negative of a vector is equal to the magnitude of that vector. Okay, so what's the third property of a metric space? Positivity, symmetry. What's the third? It's the longest. The first one is very short. The second is fairly short. What's the third? What requirements would make distances make sense? Positivity, symmetry. What else? Anyone remembers? The triangle inequality. The triangle inequality. So okay, it appears that first let's before we get to the triangle inequality. So the positivity here, positivity property of vectors. This is in the box, and here this the symmetry property of the for the vectors, for the magnitudes. So just before we get to the triangle inequality, so let's take a quick look at the 40-dimensional space, which we already did. Remember, but this time we're thinking of this as not as points, but think of them as vectors. Nonetheless, the rest is the same. So you take the difference, create this, and the absolute value of the distance. That's what it is. So we're doing the we have these numbers at the bottom given us together, and then we either add them together, which produces the taxicab norm, or we square them and then add in square root, and which will give us the Euclidean norm. So there is no difference here to speak of. So let's no difference from the point. So this is very similar to points and distances. There is no difference really to worry about. The triangle inequality. Okay, so that's the distance from P to Q plus the distance from Q to P is larger than or equal to the distance from P to Q, Q to R, and then it is larger than or equal to then the distance from P to R. We already did this a little bit. Remember that that actually the language of points can be translated into the language of vectors, which I already almost did, right? So this is equal, and this is equal, and this is equal. This is literally by that definition. There is no difference between these two. So the distance between P and Q is exactly the same as the magnitude of the vector PQ. Okay, but there is a more that we can do. What is the meaning of the vector PR? What's the meaning of the vector PR in terms of the other two? picture. PR in terms of PQ and QR. No, the average now. Not the average, but what? There's no averaging here. PQ, QR. What's the operation? Does that diagram look familiar? What? Okay, what if I deal with letters? This is A, B, and this is C. Three vectors. What's the relation? A, B, and C. What's the relation between those three vectors? Another trick question. No, the vector algebra, the algebra I'm speaking of, though we're switching to geometry, as I said, but the vector algebra, A, B, and C. What?
Is it the length of A and B?
No, way back. No. Simpler. Think simpler. Yeah, they are, but that's the starting point. Now we're trying to translate the situation into the vector algebra. Vector for vector A followed by vector B somehow produces vector C. What's how? What's the word? There's a word. A, B, C. I want to insert two symbols. Plus an equal. A, B, and C are not numbers, which is what I understand what you were speaking of. It's the length of A and the length of B added together will be larger than or equal to the length of C. That's the triangle equality. That's the essence, the triangle equality. But in vector algebra, that's what it is. The vector PR is in fact the sum of the other two. Okay, so that's how we translate the triangle inequality into vector algebra. If we are take that into account. Okay, so PR is not, if we were to abandon the points, then we got to concentrate on the algebra of vectors. And so indeed, it turns out what we adopt here is that so once again, the triangle vectors in terms of points, vectors without points, and then you realize that PR is actually A plus B. And then finally, we are assigning the magnitudes, which are the three numbers. But the third number, we're not speaking of PR anymore. It is the magnitude of the sum of the two vectors. Okay, so the magnitude of the vector, the first vector, plus the magnitude of the second vector will be larger or equal to the magnitude of the sum of the two vectors. Okay, so it looks quite a bit different from the original, but that's actually a very effective way of bringing geometry to algebra. So incidentally, you can think about what you can certainly think in terms of the geometry and the displacement. So if you were to question and maybe have some questions about the inequality, then certainly you can think about geometry, but also think about forces, for example. You understand what I'm talking about? The forces, A is a force, B is a force, and then what's the expression that is the sum is bigger than its parts, and this is the opposite, because when you have two forces, unless they're perfectly aligned, they're canceling each other out. That's what we're saying here. So Okay, so I'll try to elaborate next time. So forces cancel. Okay, okay, thank you, Joseph. Questions, Miss?